Conservative vector fields, part 3. In part 1, we defined what it means for a vector field to be conservative and found a way to determine if a vector field is conservative. In part 2, we learned how to find the potential function phi if we know that a vector field is conservative. Knowing how to find potential functions, we now investigate their properties. The first property is called the fundamental theorem of line integrals. The first part of the fundamental theorem of line integrals says that if f is a conservative vector field, then the value of a line integral of f depends only on the endpoints of the path. So if f is a conservative vector field, the line integral is independent of path, and parameterization for the path is not needed to evaluate the line integral. The second half of the fundamental theorem of line integrals says that if the line integral of a vector field f is path independent, then that tells us the vector field is conservative. If we think of phi as an antiderivative of the vector field f, then the parallel to the fundamental theorem of calculus becomes apparent. The line integral of f is the difference of the values of phi evaluated at the endpoints. Let's find this line integral where f is our conservative vector field that we saw in part 1 and 2, and where c is a simple curve from A to B. As I said, we've already seen f, and it's a conservative vector field we actually found its potential function already in part 2. By the fundamental theorem of line integrals, we know that the line integral over the curve c is equal to phi of b minus phi of a. So we're going to evaluate phi of b minus phi of a. This is a pretty straightforward process. Phi of b is equal to 5, and phi of a is equal to negative 11. So phi of b minus phi of a would have to be 16. So with our conservative vector field on a simple curve from A to B, the line integral is equal to 16. Another property of potential functions involves closed curves. Suppose C is a simple closed smooth-oriented curve, and suppose F is a conservative vector field on an open connected region containing our closed curve C. Since f is conservative, we can use the fundamental theorem of line integrals to evaluate the line integral. And since C is closed, the endpoints are equal, so the line integral over the closed curve is equal to 0. Conversely, suppose that the line integral is equal to 0 on all simple closed smooth-oriented curves in a region R. Now suppose A and B are two distinct points in the region. Let's have C1 be a path from A to B, and I'm going to have negative C2 be a path from A to B, which means that C2 is a path from B to A. Now let's let C be the closed curve consisting of C1 followed by C2. What we want to show is that both of these paths, C1 and negative C2, we want to show that both of these paths would give us the same line integral. Alright, so we make one curve from A to B, and we call that C1, another curve from B to A, call that C2. Since C is closed, the line integral has to equal 0. And that tells us that the line integral over C1 is the negative of the line integral over C2. Now, the negative of the line integral over C2 is just C2 going back the other way. And so what we have just shown is path independence, and that proves that f is conservative. Suppose C is, so here we're going to do a little summary here. Suppose C is a simple, closed, smooth-oriented curve, and suppose F is a conservative vector field on an open connected region containing C. Then the line integral over the closed curve is equal to 0. Conversely, if the line integral over closed curves are 0, then f is conservative. All right, so we have established three equivalent properties of conservative vector fields defined on an open connected region in either 2- or 3-dimensional space. So each of these properties are equivalent. There exists a potential function phi such that f is the gradient of phi. Path independence for all points A and B in the region and all smooth-oriented curves from A to B. The line integral over the curve is equal to the potential function evaluated at B minus the potential function evaluated at A. Path independence. Or equivalently, on all smooth, simple, closed-oriented curves, the line integral will be 0. And that concludes 15.3 conservative vector fields. I'll see you again in 15.4. Take care. Have a nice day.